Good afternoon, guys, and today we will discuss about the glomerular filtration system and the filtration fraction and the filtration coefficient. In the previous lecture, we have discussed about the glomerular basement membrane and some important points related to that. So let's get started. First of all, I will start with the steps of the urine formation. As you know that the urine formation involves three subsequent steps. First is the glomerular filtration step. It is indicated in the one, and here the all of the molecules present in the plasma are filtered, and including glucose, amino acids, water, ions. And after that, the tubular reabsorption occurs, where essential substances like glucose, amino acids are reabsorbed back into the blood. And third is the tubular secretion, and it can be active, like uh, potassium or organic acids and bases are actively secreted into the lumen of the tubules. So, and this diagram represents that afferent arterioles come, and the efferent arteriole is drained. After that, it forms the peritubular capillaries, and peritubular capillaries surrounds the PCT and DCT, and after that, the venous drainage occurs. Okay, so in the formula form, we can written that urinary excretion, it includes a glomerular filtration minus tubular reabsorption plus tubular secretion, because the tubular reabsorption means that substances are reabsorbed back into the blood. The glomerular filtration minus tubular reabsorption plus tubular secretion, this total is the urinary excretion, the formation of the urine. First of all, we'll discuss about the glomerular filtration system. Okay, and it is a bit complicated, but it's very easy to understand. So let's get into it. First of all, the filtration occurs, and by the it is dependent on the size and the charge of the molecules. And we have discussed about the filtration states. These are approximately 70 to 100 nanometers. Any particle or molecule that is in between that size can easily be filtered. And the glomerular basement membrane is negatively charged because of the cyanoglycoproteins and other substances like fibronectin, laminin. They impart negative charge to the glomerular basement membrane. So if the molecule is positively charged, it is attracted, and if it is negatively charged, it is repelled, like albumins. Albumin is an example of negatively charged plasma protein. First of all, what is glomerular filtration rate? It is the speed at which the filtrate is formed in the glomerular uh, capillaries into the Bowman's space. It is the speed at which the plasma is filtered or the fluid is filtered, okay? And it is the amount of the filtrate which is formed in all glomeruli per unit time, per particular time. Okay, what are the factors that affects the GFR? We will abbreviate at GFR, glomerular filtration rate. So the factors which affects the GFR are filtration forces. What are these? There are forces that favors the filtration, and there are forces that opposes the filtration. Okay, so these forces which are favoring and opposing the filtration are known as collectively the net filtration pressure. Okay, net filtration pressure is a very important term used in the GFR formula, and we will calculate it in a 1 minute. So the forces favoring the filtration, we are considering this a topic, the forces favoring the filtration. Okay, so let's come to this particular diagram. Okay, this is the afferent arteriole, and this is the efferent arteriole. This is the Bowman's space, and these are the glomerular capillaries. Okay, so there is a particular pressure in all of the arteries and capillaries which favors the which is imparted in the walls of the arteries. So it is known as the capillary hydrostatic pressure. Any hydrostatic pressure in all of the arteries in the body they exert force in the wall of the particular artery or capillary. So this pressure, what do you think? Logically, it is a force favoring the filtration because it is forcing the fluid out of the capillaries into the Bowman's space. So this force is known as capillary hydrostatic pressure, and it is the favoring force for the filtration. And in physiological circumstances, this force has, or pressure has, a value of 50 millimeter of mercury. Okay. After that, there is an other force that favors the filtration. It is known as the pressure of Bowman's space, oncotic pressure. What is it? Bowman's osmotic pressure or oncotic pressure in the Bowman's space, it is due to the proteins. It is very important point to understand that colloid osmotic pressure, or the other name for the colloid osmotic pressure, is the oncotic pressure. It is exerted due to the plasma proteins or any protein present in a particular space. So for practical purposes, the Bowman's capsule or space does not have any proteins. So according to this rule that proteins are exerting this pressure, there are no proteins. So the colloid osmotic or oncotic pressure in the Bowman space is zero in the practical circumstances. Okay. So these are the forces which favors the filtration in this direction. Okay. There are also forces that opposes the filtration. What are those forces? The proteins present in the plasma and are also present in the afferent and efferent arterioles, and these forces exert oncotic pressure in the capillaries. It is known as the capillary colloid osmotic pressure or capillary oncotic pressure due to the plasma proteins, and they have a pulling effect. Pulling effect means that they exert force in this direction, and if the force is exerting in this direction, opposing the filtration, so these forces are known as forces opposing the filtration, or GFR. The and in physiological circumstances, the plasma oncotic pressure is 30 millimeter of mercury. Okay. And there is an also other force that opposes the filtration. It is the Bowman's space hydrostatic pressure. We represent it as PBH. And hydrostatic pressure, as I have told you, that any kind of hydrostatic pressure exerts a force on the walls of a particular artery or particular capsule. So the pressure in the Bowman's space, which is hydrostatic, should exert a pressure on the walls. So this pressure is also in this direction. It opposes the filtration, and under the physiological circumstances, this pressure has a value of 10 millimeter of mercury. So we can sum up these forces. So the forces that favors the filtration is 50, and the forces that opposes the filtration is 40. So the net filtration rate, okay, the net filtration rate is approximately 10 mm of Hg, or net filtration pressure. We can also represent it as net filtration pressure. So this is under the physiological circumstances. Any pressure that is exerting in this space is either favorable or it is opposing. So under the physiological circumstances, when the urine is formed, when the filtration is occurring, normally the forces which are favoring the filtration are slightly more than the forces opposing the filtration. The Under the normal physiological circumstances, when the urine is being formed, forces which are favoring the filtration are slightly more than the forces opposing the filtration. So it's the same thing written in this theory. You can read it by pausing the video, that hydrostatic pressure of the capillary is the favorable force. The oncotic pressure in Bowman's space is also favorable. Oncotic pressure in the capillaries, which is due to the plasma proteins, it is opposing force. And the capsular hydrostatic pressure, it is also an opposing force. So adding all these forces, we reach up to this value that 10 mmHg is net filtration pressure. Okay. And according to this formula, the net filtration pressure is equal to forces favoring the filtration minus the forces opposing the filtration, and we get the term 10 mmHg. Okay, the next factor we need to understand is the filtration coefficient. What is filtration coefficient? It is determines how much filtrate is produced, and it is based on two things: the total conductivity or permeability of the filtration barrier, and the total surface area of the glomerular capillaries. It is very important to understand that filtration coefficient, which is represented by Kf, it is nothing but it determines how much filtrate is produced in ml, in milliliters. Okay, we will discuss in a bit detail in later. So it depends on two things. First is the total surface area for the glomerular capillaries, and the second is the filtration barrier permeability or conductivity. Okay, as we have discussed in the previous lectures that the glomerular capillaries have a unique features because it is a system present between two arterioles. It is a high pressure system because in other parts of the body mostly the arteries are drained into the veins, but in these circumstances the artery is draining into an arteriole. Okay, so this creates a high pressure for the filtration, and we need that in the kidneys as far as kidney is concerned. Okay, filtration fraction. As I've discussed a little bit that filtration fraction, the name suggests that fraction of the renal plasma flow through the glomeruli. It is known as the filtration fraction. It means that fraction of the plasma flow which is being filtered through the glomerular filtration system. Just focus on the term fraction and you will understand the definition, that amount of the plasma that is being filtered through the glomeruli. In all of the glomeruli of the kidney, approximately 2.6 million nephrons are present and 2.6 million glomeruli are also present. So this is the filtration fraction, which is the fraction of the renal plasma flows through the glomeruli. Let's discuss about how much is the filtration fraction, and we can determine it. Okay, just concentrate. First of all, the cardiac output is 5 liters, and we have discussed in the previous videos as well. Cardiac output is 5 liters. Out of the 5 liters, approximately 1 liter or the 20% of the cardiac output goes to the renal artery for the filtration purposes. Okay, and 1 liter of the blood contains plasma and cells, RBCs, WBCs, and platelets. As you know that the cells of the blood, like erythrocytes, leukocytes, and thrombocytes, they have size enormous as compared to the filtration system. So these are not filtered at any cost. Apart from the diseases which are hematuria, we can found RBC in the blood, but under normal conditions the cells are not filtered. So from 5 liters, 1 liter goes to the renal artery, and from 1 liter, 600 milliliter is plasma and 400 milliliter is the cells. So forget about the cells, and just keep in mind that we are talking about 2.6 million nephrons right now, not single one. 2.6 million nephrons in both kidneys. Okay, we are talking about that. So 600 ml plasma is comes towards the glomeruli, which are 2.6 million nephrons. From 600 ml plasma, 20% of it is filtered. 20% is filtered, and the remaining go unfiltered. Okay, and 20% is equal to 120 ml. This is the plasma fraction of the plasma that is filtered per minute in all 2.6 million nephrons of both kidneys. So filtration fraction is nothing but the amount or fraction of the plasma that is filtered in ml per minute in both kidneys. According to the formula that GFR glomerular filtration rate divided by the renal plasma flow, we obtain the filtration fraction. So what is the glomerular filtration rate? Glomerular filtration rate is that the uh, filtration of the plasma, so it is 120 ml. Okay, 120 ml divided by 600. Why we divide it by 600? Because the amount of plasma coming towards the kidneys, both kidneys, we obtain a number which is 20%. So 20% is the filtration fraction. Okay, it is very easy to understand when you follow the sequence that from the 5 liter, 1 liter goes towards the kidneys. 1 liter consists of 600 milliliter plasma and 400 milliliter of the cells. From 600, 120 ml is filtered. The remaining 480 ml goes unfiltered. 120 ml is glomerular filtration rate, the rate at which the plasma is being filtered per minute. Okay, and from the formula, filtration fraction can be calculated: GFR divided by the renal plasma flow, which is 600, and we obtain a number which is 20%. It is the filtration fraction. Okay, after that, what is filtration coefficient? As we have discussed earlier a little bit, that Kf represents amount of fluid filtered in ml per millimeter of mercury of the net filtration pressure. Okay, it is the amount of fluid filtered in ml per millimeter of mercury of the net filtration pressure. The filtration coefficient, which is represented by Kf, depends on two things. First is the conductivity, hydraulic conductivity of the glomerular capillary membranes, which is the permeability, and the second is the total surface area. When we increases the permeability due to any condition, we increases the filtration coefficient. And when we increases the total surface area for the filtration, we increases the filtration coefficient. Okay. And the formula for the filtration coefficient is hydraulic conductivity multiplied by surface area for the glomerular capillaries. So, summing up all the things, we obtain that the glomerular filtration rate GFR is directly proportional to the net filtration pressure. And what was the amount for the net filtration pressure? It is 50 minus 40. 50 is the forces favoring the filtration and 40 is the forces opposing the filtration, and we obtained 10 millimeter of mercury. And GFR is also directly proportional to the filtration coefficient. And we can find the filtration coefficient by using this formula. GFR is equal to net filtration pressure multiplied by Kf. So we can divide the GFR divided by the net filtration pressure. What was GFR? GFR was 120 ml, as we have used in this formula as well, and net filtration pressure is 10 mmHg. So 120 divided by 10, we obtain a number which is 12. What are the units of it? Units are 12 milliliter by mmHg by minute. So it means that filtration coefficient means 12 ml of filtrate is produced per 1 mmHg of pressure per minute across total glomerular surface area, which is 2.6 million nephrons, which means all of the renal substance. Okay, and this number, which is 12 ml, it is for both of the kidneys. And you know that both of the kidneys have the weight of approximately 300 grams. Both kidneys have the weight of 300 grams. And when we want to find the Kf for 100 gram of the renal substance, we can just use the equation like For 300, the Kf was 12 ml per mmHg per minute, but for 100 we can just cross multiply them and we obtain a number of 4, which is 4 ml per mmHg per minute by 100 gram of the renal substance. Okay. After that, there are some diseases or conditions that can affect the conductivity of the glomerular capillaries and also the surface area. So let's talk about the permeability. In diseases like diabetes mellitus, proteinaceous material are deposited and they causes the thickening of the glomerular capillary membranes. And logically, when the capillary membrane become thickens, it reduces or increases the GFR. Of course, it reduces the GFR because it is directly proportional to the filtration. Okay, when we thicken something, the filtration is of course reduced. The second thing is the high blood pressure. It also reduces the GFR significantly. For surface area, there are two diseases you need to keep in mind. First is the glomerulonephritis. Second is the pyelonephritis, and both these are chronic conditions. In both conditions, it leads to the scarring and loss of the glomeruli, and it reduces the surface area. When the surface area is reduced, of course, the GFR will be reduced accordingly. I know that this all was very messing up in your head, so let's revise a little bit. First of all, the GFR. GFR means that the speed at which the fluid is filtered, and it depends on two things. First is the net filtration pressure, and second is the filtration coefficient. Net filtration pressure we obtained by summing up the forces favoring the filtration, which is 50, and opposing the filtration, which is 10. So which is 40. We obtain a number which is 10 millimeter of mercury, and it is net filtration pressure about filtered per mmHg in 1 minute of the renal substance. And you know that the filtration coefficient depends on two things. First is the permeability, and second is the surface area. Okay. And about this we can also revise a little bit, that from the cardiac output of 5 liter, 1 liter goes to the both kidneys, and from 1 liter 600 is plasma, and from 600 120 ml per minute is filtered, and this 120 ml per minute is known as the GFR. Okay, GFR. And this GFR is very important in calculating the filtration coefficient. Okay, after that we can calculate the filtration coefficient. Net filtration pressure we know, which is 10, and GFR we know, which is 120, and according to this formula we obtain a number of 12 ml per mmHg per minute. It is for both kidneys. Both kidneys means that 300 gram of the renal substance. For 100 gram we can just cross multiply and we obtain 4. 4 ml is for the 100 gram of the renal substance. I hope you understand these terms. These are very easy to remember. The pressures, the forces, the filtration fraction, the filtration coefficient, these are not very misunderstandable, but these are very easy to understand if you concentrate. And this was for today, and after in the next video um, we'll discuss about the remaining parts of the glomerular filtration rate, and I will see you in the next video. Till then, goodbye.